So the first thing I want to talk about is one of the early experiments. This is J.J. Thomson in 1897. Basically, what he was doing here was taking this cathode here. So what this is just different types of metal he would use. Okay, and he's got a high voltage source, and this screen over here is just to help detect things. So things like radiation and charged particles will leave a mark on that screen, so he can figure out, where it hit, how much it's been deflected, or something like that. It's basically like a cathode ray tube. Is what is a cathode ray tube. We used to use cathode tubes in televisions before the integrated circuit came along. We went to that, and tubes went by the wayside. So by applying this voltage, he gets this beam of particles. And because he's got these, kind of magnetic fields here, and he's applying this electrical current, he's able to determine, and you can see here, he's also got electrically charged plates, so one here and one here. He's able to determine that this particle, which we now call the electron, is positively charged because we know that opposites attract, and you can see that this particle was attracted towards the positive plate. So that's how he determines this particle is negatively charged. Okay? Now, with these electric and magnetic fields, he can do a bunch of physics calculations, okay? And it's way beyond this class, this level. You might cover it in physics, actually. I don't know what kind of detail they go into this in physics. But anyway, there's these electricity and magnetism equations, and you can use kinetic energy equations and potential energy equations and solve these equations for what we call the charge to mass ratio. That would be the charge of the electron, and that would be the mass of the electron. He was able to get this charge to mass ratio. He couldn't tell you what either one of them was, either the charge or the mass, but he noticed that the ratio of the charge to mass was always the same. So this electron beam, if you will, when you got this deflection, the extent of that deflection, if you will, and he could calculate momentum and things like that, and momentum you might know is mass times velocity. You could get the velocity. With all these calculations and equations, he showed that the charge to mass ratio was always the same, and it didn't matter what material was used here metal-wise, which led him to the conclusion this was a fundamental particle that was part of matter. Okay? Now Millikan comes along, and he has this knowledge of charge to mass ratio, and he sets up, this is one of my favorite experiments. It's just a brilliant experiment. So he's got these oil drops, and this is called an atomizer. It just means that we're going to spray these oil drops, going to make them very small. It doesn't mean they're sizes of atoms. They're still going to have, hundreds to thousands of atoms to make up a little droplet. But that's the idea. Small little droplets that will fall through this hole. And he's got these positive and negatively charged plates. And of course, he has a microscope here to look at these. And he's got X-rays so he can ionize the particles. So by shining the X-rays on it, he can actually ionize the particles, give them a charge. Now, X-rays, and that's something that's a little bit beyond right now. It's not beyond your understanding. It's just not appropriate to talk about it now. But that's an ionizing radiation. Ionized radiation can dislodge electrons from matter. That's what makes X-rays somewhat dangerous, not to get too many X-rays and other types of electromagnetic radiation. So he's able to impart a charge to these oil droplets. And he could also measure the charge to mass ratio, just like Thomson did, so he can confirm Thomson's work that charge to mass ratio was constant. And of course, the droplets are falling now under the force of gravity through here. Now, because we know Newton's laws at this point, those were a couple hundred years earlier, he knows the rate at which the oil droplets should fall under gravity. So by adjusting these fields here, right, he can control the rate at which it falls, because if these particles are negatively charged, which Thomson determined, they're going to be attracted towards this positively charged plate, and therefore he could slow the rate at which it falls effectively. And the extent to which that changes allowed him to be able to calculate the charge on the electron, because the slower it would fall, the greater the negative charge. And once he calculates the charge, then obviously he can calculate the charge to mass ratio, because we've already know what E over M equals. If he calculates E, then he can figure out what M is. So that's what allowed him to get the charge and the mass of the electron. Now, Thomson comes up with this model. It's called the plum pudding model. I've personally never had plum pudding, but you can relate to the idea possibly that it's just a big swirl of matter. Okay? And, protons weren't discovered yet, but we knew matter was neutral because matter had no charge. So if matter has electrons as a fundamental particle, there must be something balancing the charge. There must be this positively charged sphere, if you will. Okay? Not really defining it much. And electrons are embedded within that positively charged sphere. This is the plum pudding model. Okay? So, we need to introduce radioactivity, which is on my outline, before we go into Rutherford's experiment. So, this was somewhat serendipitous. So he found that pitchblende, which is one of the uranium ores, so uranium basically, produced invisible radiation. He basically was storing this pitchblende in like this, lab drawer. And in that lab drawer, the story goes, he also had some photographic film. And, I grew up taking film photography, but if you work with X-rays, you know about exposure of film produces, an image. It's no different than what he's doing here with this phosphorescent screen, right? Exposure produces some sort of image. So he noticed he pulled out the film and it was exposed. And he was like thinking to himself, well, someone must have let some light in, right? But then it happened again and again. So he started to think that this pitchblende was actually causing this exposure. It was giving off some sort of radiation that was invisible. Okay, and, the Curies, of course, big group. Marie Curie, one of my favorite scientists of all time, brilliant woman, did her work on radiation, lost her life because of that, got leukemia, won 2 Nobel Prizes, just one in chemistry, one in physics, just a brilliant woman. So we had this stuff was giving off particles, if you will, and beta and alpha, those are the symbols, and beta particles are basically high-speed electrons, but don't get confused. We don't need to go into this now. They're not the electrons that are, well, we haven't even introduced that, are in the valence shell, if you know that term, around the nucleus, okay? These are actually being generated from the nucleus. Tough to understand right now, but just trust me, they're generated from the nucleus. They're particles, because physics knows that the nuclear particles, protons and neutrons, are not the simplest of particles. We can break those down to smaller particles, things like, quarks and gluons, mesons, bosons, all this type of stuff. So it's coming from the nucleus. And alpha particles basically have the same mass as a helium nucleus. They're basically 2 protons and 2 neutrons. Of course, we don't have protons at this time. We haven't discovered them. But that's what we know now. So just take these as high-speed particles, okay, that come from the nucleus. So he uses this material, puts it in this lead box with a hole, and expose it to this thin piece of foil. And he used gold because gold was very malleable, can be pounded into these really thin sheets. And what he was doing was testing the plum pudding model. And his hypothesis was, we talked about the scientific method, right? His hypothesis was, well, these nuclear particles that are being shot at this, these alpha and beta particles, are more massive than this. Certainly the alpha particles, right? That's the main thing he's looking at here, these alpha particles. And therefore should if they hit this, maybe deflect slightly. And for the most part, since this is just electrons dispersed throughout this positively charged sphere, these alpha particles should, for the most part, just go right through. And effectively, it's kind of what he saw. Most of the particles went straight right through, and he detected it on this screen, this fluorescent screen behind it. Occasionally, they would be deflected slightly, which also made sense. But then this is what woke him and his graduate students up, was the fact that, I actually think there was an undergraduate working on this too, that there were some of these that looked like that had bounced off of hitting something really solid. And in fact, the title of this section in your book is When Projectiles Bounced Off Tissue Paper, the Rutherford Model of the Atomic Structure. And the idea here is if I take a shotgun and someone was holding a piece of tissue paper and I shot that, or not even a shotgun, just a a handgun bullet, and that bullet bounced off that tissue paper. That's kind of what they were seeing here. This is amazing what they were seeing. They immediately said, well, this can't be the correct model because there's nothing that would cause in this model this to happen. There must be some sort of massive center to cause an alpha particle, which I can tell you is going to weigh something like 2,000 times, it's even more than that, heavier than any electron. So this coming close to this or hitting this even head on should not cause this type of deflection because it's much more massive. So he comes up with a new model, and we're going to talk about that a little bit in class. So I want you to think about that model. Ultimately, protons are discovered, and he comes up with this model. Neutrons are not discovered. He discovers the proton also. And he comes up with this model. And then, of course, we've got these, basically, in these units we're going to use, atomic mass units. We'll introduce that a little bit later. This is the weight of a proton and neutron are about the same. You notice the electron is much lighter. And these are, if you will, the kind of normalized mass numbers we use to just put things in simple terms. And the masses of atoms and subatomic particles are expressed in unified atomic mass unit, equal to 1/12 the mass of a carbon atom. And that's because carbon has 6 protons and 6 neutrons, so it works out nicely. This is done for convenience. We create this unit of U so we don't have to deal with exponents like this in our periodic table and in comparing numbers. It's really for convenience. Okay? And then we come up with this way to just symbolize these things. And what we have here is the element symbol. So if you had carbon, it would be C. And the top number is the mass of the nuclide, and the bottom number, the nuclear charge or the atomic number, which is the number of protons, if you will. So for carbon, you might see something like this. That's the number of protons, the atomic number, which is the signature of the atom. If it has 6 protons, it's carbon. If it's carbon, it has 6 protons. No exceptions to that. The mass number can change. That's the number of protons plus neutrons. Neutrons aren't discovered until by Chadwick until 1932, I think it is. So that tells you the number of protons plus neutrons. So obviously 12 minus 6 equals 6 neutrons in this particular nuclide. Okay, we'll talk about isotopes in class. I want you to read a little bit about isotopes, know what an isotope is as we come into class. And this is the symbols that we use. All right, the second to last topic, we'll introduce the mole at the end. The second to last topic here is this video is going to run a little bit longer, probably closer to 30 minutes, well, maybe 25. Elements are ordered by increasing atomic mass in Mendeleev's periodic table. Gets the credit with basically the first periodic table. He increased them by atomic mass, okay? And here we've got the atomic mass above the element. Remember, protons aren't discovered at this point. Mendeleev's table's before that. So the masses are above it, and he orders them in order of increasing atomic mass. And what he does is he arranges them in columns so that they have similar properties. So the idea was, instead of putting sodium out over here, he puts it down here because it was similar to lithium. He starts a new row, if you will. Okay? And he left spaces where there were no elements. And sure enough, he actually predicted that, hey, we'll discover an element that's going to, and there's no showing any gaps here. They didn't leave any gaps here to show that. I think silicon was one of the ones he predicted. Oh, here's one right here. So trying to remember what 44 is. I think it's ruthenium. Anyway, so Sorry, just looking for a periodic table with the names on. I still struggle with a couple of the names actually. Um, so 44 is one that he predicted would be discovered and things like that, and he would actually predict some characteristics of it too. They were pretty darn close. So it was pretty amazing. Well, now we know with the modern periodic table, though, we're going to arrange them in order of increasing atomic number once protons were discovered, because that's one of the keys, because the atomic number, the number of protons, equals the number of electrons, and the electrons are really what determine that chemical and physical property for the most part, besides things like density. So that makes more sense. And there are a few cases where they had to be changed. For the most part, as the atomic mass increases, the atomic number increases, but not completely. There are a couple cases, and you can find them on a periodic table. I'm not going to take the time on the video to do that now. And here's some categories. So these kind of bone-colored ones are your metals. So most of the elements are metals. The non-metals represent the blue ones, and this represents most of the structure of biological materials, which we build things from. Most of the universe is going to be non-metals because most of the universe is hydrogen followed by helium, because stars are mostly hydrogen and helium. They make up by far most of the mass of the universe. You look at the numbers, our sun represents something like 99.8% of all the mass of the solar system. But when you look at living matter and things like that, it's going to be mostly non-metals. When you look at stuff like rock and bulk matter, the structure of the earth, if you will, it's going to be mostly, well, no, I shouldn't say mostly, because there's a lot of oxygen in that. Oxygen is one of the main elements, and silicon's a major element within the structure of minerals and things like that. But you have a lot of metals. That's where you find a lot of your metals and stuff. And of course, there's metals in biological material. They serve as catalysts. We got metals that build our bones, right? Calcium. But what you think about carbohydrates, proteins, nucleic acids, these are mostly non-metals, your biological molecules. And metalloids, of course, have characteristics in between metals and non-metals. You think about metals, you think about malleable and ductile, right? And conductors of electricity and heat, things like that. Metalloids are going to be in between that and non-metals. Something you need to start to get familiar with, and this will come back numerous times within the class, is this trend of charges within the periodic table. I'll talk about this a little bit in class, but you notice that group 1 is +1 and group 17 is -1. And that'll become clear why later as we go into chapter 3. It doesn't mean these are the only charges available. Why that is true in group 1 for the most part, I can make sodium +2, but it's not very common. But over here, you could have lots of different charges for some of these elements, even under fairly simple conditions. Something like sodium, for me to get to 2+ cation, takes a lot of energy and under specialized conditions. But these are common ions we find in nature and in life and the way they form. So start to get familiar with those. And these are, of course, the groups. This is one I never learned. They didn't use this, or they didn't teach it back when I took it, the chalcogens, but all the others, the other 4 are very common, so get familiar with these. And then lastly, I want to talk about the mole, and this is how we're going to finish up. And I want to express to you that I truly believe that this is not as complicated as students make it. And I want to say to you that, in fact, that a mole is exactly the same as a dozen, only a different number. Exactly the same. A dozen apples is the same as a dozen ping pong balls in terms of number, 12. A mole of hydrogen atoms is exactly the mole of carbon atoms, 6.02 times 10 to the 23rd. Do they weigh different? Yes. A dozen ping pong balls weighs a different amount than a dozen golf balls. So if you imagine the periodic table had ping pong balls, PP for ping pong, and golf balls, ping pong and golf balls. And they had a number underneath those that told you the mass of a dozen. That's what our periodic table is. Okay, now I don't have a periodic table here that has the actual masses on them. Eventually we'll see ones with a mass down here, right? But if you look at that number, it's the mass of a dozen. Only difference is the mass of 6.02 times 10 to the 23rd. So imagine the periodic table is just that. And if I asked you, what's the mass of one ping pong ball, and I told you the mass of a dozen, you'd easily do that and divide by 12. Well, if I ask you now, what's the mass of one carbon atom? Well, you'll simply go to the periodic table, look at the atomic mass of 12.01, and you divide that by 6.02 times 10 to the 23rd, and you'll get your answer in grams, because this really means grams per mole. So you'll see it in two different units, because it's really 12 AMUs. That's the weight of one carbon atom. Okay? But it's also the weight of our dozen in grams. That's why we did this. We did this for convenience. We structured it this way. So a hydrogen atom weighs 1/12 of a carbon atom and therefore weighs 1 AMU. So you can imagine this. If I told you that a golf ball weighs 12 times more than a ping pong ball, right? Then you would surmise that a dozen ping pong balls weighs 12 times a dozen golf balls. Oops, I said that backwards. A dozen golf balls weighs 12 times a dozen ping pong balls. No different. A mole of carbon atoms weighs 12 times a mole of hydrogen atoms. One hydrogen atom weighs 1 AMU. One carbon atom weighs 1 AMU. A mole of carbon weighs 12 grams per mole. A mole of hydrogen, I'll make this hydrogen and carbon here, weighs 1 gram per mole. That's what we did. We structured it all based on carbon and then did everything relative to carbon. That's the beauty of it. You now look at the periodic table. You always know the mass of a chemist's dozen, which is 6.02 times 10 to the 23rd. With that, the video's a little over 20 minutes, 22, 23 minutes. I want to stop there and say we're going to spend a lot of time on the mole. This concludes your Chapter 2 video.